We hear that word algorithm thrown around everywhere these days. But what is it really? And maybe more importantly, how do we know we can actually trust one? Today, we're going to go way beyond the buzzword. We'll uncover the hidden logic that powers so much of our world and find out what it really takes to prove that it's correct.
So, to get our heads around this big challenge, let's start with a problem that, well, on the surface, it looks incredibly simple. Take a quick look at this list of numbers. If I asked you to find the total sum, how would you do it? I bet most of us would do the exact same thing, right? You'd start with 12, then add -4, then add 5, and so on until you hit the end of the list. Seems pretty straightforward.
That step-by-step process you just pictured in your head, well, that is the very heart of an algorithm. Computer scientists take that idea and formalize it into a super precise set of instructions. You can think of it like the perfect recipe for a computer to follow. Now, a formal algorithm is way more than just a suggestion. It's a finite sequence of well-defined instructions. That means every single step has to be crystal clear, with no ambiguity at all. And it's designed to solve not just one specific little problem, but a whole class of similar problems. It's kind of like the ultimate recipe. So here's what our little recipe looks like written down in something called pseudocode. Now, this isn't a real programming language. It's more like a middle ground, a way for us humans to read the logic without getting bogged down in code syntax. And the logic is simple. Start a running total, sum, at 0. Then, for every single number in the list, you add it to that total. When you're all done, you just return whatever that final sum is. Okay, let's walk through this with our list. Programmers call this a dry run. The very first instruction says to set our running total, our sum variable, to 0. Easy enough. Now the loop kicks in. We grab the first number, which is 12, and add it to our sum. So 0 plus 12 is 12. Our total is now 12. On to the next one. We've got -4. We add that to our current total of 12, which brings the sum down to 8. The third number in the list is 5. We add that to our 8, and we get a new sum of 13. And finally, the last number, 9. We add that to our 13, and our sum becomes 22. There are no more numbers left, so the loop is all done. The recipe's last step is to return that final value of sum. So the algorithm spits out 22. And hey, if you add them up yourself, you'll see that's exactly right. Fantastic, our recipe works. Or does it? See, here's the crucial question. We've only shown that our recipe works for one list. How in the world can we be absolutely sure it works for every possible list? And this question is what separates just, basic coding from the real science of algorithms. Was our recipe just lucky with that one list, or is it fundamentally mathematically correct no matter what we decide to throw at it? Let's think about some of the tricky situations, what developers call edge cases. What if the list only has one number in it? What if all the numbers are negative? What if the list is completely empty? Or what if it's huge, with 1,000,000 or 1,000,000,000 numbers? Is our simple little recipe going to hold up? Sure, we could sit here all day testing different lists, but here's the massive problem. The number of possible lists of numbers is literally infinite. We can never, ever test them all. Testing might give us confidence, but it can never give us absolute certainty. So if we can't test our way to certainty, what's left? The answer isn't more testing. It's using the elegant power of pure mathematical logic to build an unbreakable proof. And the secret weapon for this is something called a loop invariant. Now, don't let the technical name scare you. It's really just a simple statement of fact about our algorithm's loop that is always true. It's true before the loop even starts, and it stays true after each and every time we go through it. It's like a golden rule. So, for our summing recipe, the golden rule is simple but really powerful. It's this. After each step, our sum variable correctly holds the sum of all numbers we visited so far. Just think back to our dry run for a second. That statement was true at every single step, wasn't it? Proving this works exactly like a chain of dominoes. First, you have the base case. You have to prove the first domino will fall. For us, that means proving our golden rule is true before the loop even starts. Well, the sum is 0, and we haven't visited any numbers, so check. Then you have the inductive step. You have to prove that if any domino falls, it's guaranteed to knock over the very next one. This means showing that if our sum is correct after visiting, say, 5 numbers, our logic for adding the 6th one must also be correct. And it is. Check.
So if the first domino falls and every domino knocks over the next one, we've just proven that the logic holds for the entire chain. It doesn't matter if there are 4 dominoes or 4 billion. Now, this isn't just some neat academic trick. This level of logical certainty is absolutely, fundamentally essential to the world we live in today.
It really all comes down to this core difference. Testing checks a few examples, and yeah, it might find some bugs. It gives you confidence, but a mathematical proof, it guarantees all cases. It doesn't just give you confidence, it provides cold, hard certainty.
And that certainty isn't just a nice to have, it is non-negotiable in the systems where failure could be catastrophic. We rely on provably correct algorithms for the banking systems that handle all our money, for the flight control software that keeps airplanes safely in the sky, for life-saving medical equipment, and for the probes exploring the most distant corners of our solar system.
So that brings us to one final thought. The next time you use a critical piece of technology, you swipe a credit card, you get on a plane, ask yourself, which would you rather it be built on? A test that shows it probably works, or a proof that guarantees it always works? Because when it really, truly matters, confidence just isn't enough. You need certainty.